I want to kick it off by making a statement about what does a world-class mechanical contractor look like. So I printed it out for you, and I'm just going to read it down, and I may pause at certain points just to accentuate it, but please follow along with me. Creating a world-class organization in the plumbing and HVAC contracting and service industry requires a strategic approach and a commitment to excellence. The following list is what a world-class organization in this field should look like to our clients, to our associates, employees, and management. This is what we at EMS are seeking to achieve, and I'm glad you all have taken the time out of your busy schedules to advance EMS and yourselves in your careers here and the company as a whole in this endeavor. So first on the list is exceptional customer service. I don't know if any of you guys go to Stu Leonard's, but if you see the rock at Stu Leonard's, what's on that rock? Customer's always right. Rule number 1, customer's always right. Rule number 2, refer to rule number 1. When in doubt, refer back to rule number 1. I don't go to that degree because the customer doesn't necessarily is not always right. But the point is made is that we're to treat our customers with exceptional service. That's really the point. So providing outstanding customer service should be a top priority. This includes prompt responses, clear communication, and going above and beyond to meet customers' needs. So I'll give you an example what that might look like. You walk into a site, let's just say it's a GC, you're working on a construction project and you're working in an area and it's got crap all over the place. And you're gonna work in this environment. First of all, it's not safe. So you need to get it cleaned up so it's safe for yourself. The point I wanna make is leave the place better than what you found it. In any environment that you're working in, leave it better than what you found it. It's a small thing, and it'll set the customer and go, wow. They'll go, wow, it's a wow factor. And when you get a wow factor, Dave can tell you this, that it makes them want to have you come back. And that's what we want. We want people to want us. Listen, anybody down the street can be a mechanical contractor. We want to be set apart. We want to be world class. So even in the small little details like that, think about that. What would you want for someone to do for you? It doesn't cost that much in terms of time. Plus it's safe. So think about that. That's just one example of what exceptional customer service might look like. Number 2, highly skilled team. Well, to have a team, you have to have individuals. And the individuals need to be highly skilled in order to make a highly skilled team. Employing a team of highly skilled and certified professionals who are experts in plumbing, HVAC, and customer service. Continuous training and development is our key focus, which is why we're doing this today. Cutting edge technology, number 3, utilizing the latest technology and tools in the industry to provide efficient and effective service. This includes advanced plumbing and HVAC equipment, scheduling software, and digital communication platforms. Number 4, quality workmanship. Delivering high quality workmanship on every project. Whether it's a small repair or major installation, attention to the details and a focus on craftsmanship are essential elements. Number 5, cost consciousness. Being cognizant of the principle that time is money. We strive to provide tools and equipment that will save on labor so we can all do our work in the most efficient manner. Good time management is essential in a world-class environment. Safety first, prioritizing safety in all aspects of the business, including on-site practices, equipment maintenance, and employee training, ensuring compliance with industry safety standards and regulations, which is why we have our monthly training with Adam and your weekly toolbox meetings. Number 7, environmental sustainability. Incorporating environmentally friendly practices and products into our operations, such as energy efficient HVAC systems and water saving plumbing fixtures, promoting sustainability and responsible resource management as part of a world-class environment. Number 8, 24/7 emergency service, offering round-the-clock emergency plumbing and HVAC service to provide immediate assistance to customers in urgent situations, being reliable and responsive in times of need. Number 9, strong ethical standards. That probably should be at the top. Building a strong reputation in the industry through positive customer reviews, referrals, and testimonials, upholding high ethical standards and fostering trust with clients and partners. And last, community engagement. Engaging with the local community through supportive initiatives, sponsorships, and education programs. Being a responsible corporate citizen and giving back to the community, which is something we're going to be doing more of in the future. Our mission statement is right at the bottom, and this is something I want to keep in front of your thought process is this. Serving others with utmost quality is EMS, and you can change the name from EMS and put your own name in there, is EMS's chief concern. It's your chief concern. It's something I want to hold you to. We want you to do your best, your utmost. And I'll give you a brief underpinning of what quality means. Quality means being honest. That's number 1. Always be honest. Even if it hurts. You'll never get in trouble for being honest with me, ever. Being a man of integrity. Doing the right thing when no one's looking. You don't have to have anyone looking over your shoulder. I want you to do it right because you want to do it right. So I want that to be your thought process. I want to be a man of integrity. Selflessness is another element of quality. Being selfless. Serving others, is part of that. Professionalism. Being professional in your communications with your subcontractors, with your vendors, with your coworkers. Using vulgar language, getting a little heated, that's not professional. Calm it down, take a breath, walk away, whatever you gotta do to calm yourself down, but be professional in all your communications and then in your interactions with people and with your coworkers. And then there's one other one that I've just recently added, and that's called forgiveness. We live in an imperfect world. We're all gonna make mistakes. Even I make mistakes, and I even wrote a letter. You saw the mistake I made with Marnie the other day here. And be man enough to admit it. And be humble enough to reconcile. That's a key quality of a good working and sponsoring or not sponsoring, but endeavoring to have a good working relationship. You need to be humble enough to be able to say, hey, I was wrong, or reconcile with someone who you may not be getting along with. Very important. I don't want to have this within the company. I want harmony, and I want you guys to have fun working. And part of having fun is being able to enjoy the people that you're working with. And you could be working with one guy one day and another guy another day. It's going to be intermingled. I can't say, I can't put Henry with say Jim because they don't get along with each other. No, I got to be able to have the responsiveness has to be really good so that I can actually mix people around on jobs. We have to have that capability, and we don't want to put people in situations where they're not happy or uncomfortable. So if you can't resolve anything by being humble and forgiving, someone could come to me and we can resolve it. And I want to resolve it in a good way. So that's some of the aspects of quality. I mean, if you go to the website, you'll see I have that mission statement there, and I have all the core values that flow into that mission statement. If you want to look at it, it's there in writing. All right. So some of you guys don't know me because you know, come from different places recently, whatever. I'll just give you a brief synopsis, or not a synopsis, but a little history of me. I was born and raised in Grand Rapids, Michigan. My father was a plumber. My grandfather was a plumber. My grandfather had a very successful plumbing and HVAC business in Michigan. And he went and bought a bankrupt general contracting company in Kalamazoo, which is like an hour away, and did it just so that he could start another mechanical contracting company. And he sent my dad's brother, his brother, and another guy down there to start the company. It was called Associated Mechanical Services, AMS. They built that company into a powerhouse. It was on the domestic engineering's list back in the 70s. It was in the top 50 in the country. They were big, and they did a lot of stuff. They had a sheet metal shop that was twice the size of this thing, and could do scullery sinks. They did all kinds of stuff. They made lots of things. So that was my background. That's where I came from. I thought I was going to work my way up into management with my dad's company. When I got out of high school, I was actually going to go to college. Then I started working for my dad, and that summer I go, I'm not going to college. I'm just going to work my way up like he did in the field. I did that, and then my dad had a parting of the ways with his brother and everybody else, and he moved 4 hours away, started another company, and that company kind of went broke because in Michigan at that time the economy was really going into the tank. So he lost it all. He could have lived happily ever after and never had to turn a wrench ever again in his life. But he started that company for me and my brother. At least that's what he told me. He said he did it for that reason. And then it went broke. He lost everything. Came out here. That's how I got out here. Actually, he moved out here for another company. Worked for Tompkins Beckwith out of New York. And yeah, so John was still living at home. I was married at the time. They wanted to hire me to be a project manager or whatever. I came out here and interviewed, and I remember driving down the Taconic Parkway, and I told my wife, I'm never moving out here. It's just too many people out here. So we went back to Michigan, and I was in the union at that time, and I was a steam fitter. So I was welding at a nuclear power plant for Bechtel Power for several years, and so I was doing certified welding nuclear power systems. And then I became a field engineer for the other, there were two contractors. There was Bechtel Power and there was Babcock and Wilcox on this nuclear power plant. And I became a field engineer for Babcock and Wilcox for a year. And I got laid off because the plant was shutting down. They had a way, when 3 Mile Island happened, this was a sister plant to 3 Mile Island, and it became, instead of being a $60 million project, it became somewhat like a couple $2 billion project, and almost broke the utility. So I got laid off, and then I moved to Oswego, New York, which is like 4 hours away. Became a welder for Johnson Controls. And then my dad called me up one day. He goes, hey, you want to go back in business? And I said, let me think about that. And then I called him back and said, yeah, I'll do it on one condition. If you give me equal say in the company, I'll do it. So I said, okay. And the rest is history. So I came here in 1985, and me and my dad and my brother started the company. And I can just remember looking out the window at my condo the first year. I go, I wonder where I'll be next year. It was, we didn't have no capital. It was, my Buick Skylark was our first truck. Our first job was in Queens, New York, doing underground for the Moonies, actually. It was a big world press building. We did 12-inch, extra heavy, lead and oakum, cast iron on down. All the underground was extra heavy cast iron. Back in 1985, I came from Michigan. Everything was PVC in Michigan. We didn't use cast iron like that. Anyway, that was our start, and here we are today. And it's been quite a ride. I love every minute of it, and I love the people that work here. And I want to foster a very family-oriented type of relationship with the men and women that work here. I want this to be you're not a number, you're a valuable human being made in God's image. And we need to care for one another. And that's where I'm coming from. So, my brother's very aligned, and we're both aligned very well in that regard. We love the Lord, and we love people. And that's where we're coming from. So, there you have it. That's me in a nutshell. Ed, I don't need to introduce him, but I'll let him introduce himself.
And good morning, everybody. Listen, thanks for coming. I want to just start off with an introduction. It's not in your books, and you don't really have to read along. The information you have here, if you want to look at it while I'm talking, it's just that you have kind of what I went over, okay? So, you say, why would a company want to do this? As you work and you put many years in the business, you gather some knowledge. Do you know everything? No, you don't know everything, but you do learn something. So this is something I've been wanting to do for a long time, and if you pick up one or two things, 3 or 4 things that I say through this part of my session of the training, then that'll make me feel better, and hopefully it makes you a better HVAC mechanic. I'm not a plumber by trade. I don't have a trade license, but I went through the engineering side of things. I work for a consultant. So this is the reason why we're doing it. We want to impart some of our knowledge onto you guys. If we help educate our workforce, maybe you'll gain some insights when you're out at a job. And you can say, okay, I kind of understand why they selected this system. And on the service end, you might be able to say, all right, there's something going on. Instead of just going and replacing the board on the unit, a place I used to work with, I couldn't tell you how many boards they replaced. I have a hard time believing that many boards were bad. But you might be able to sit there and say, okay, I know how this works. Maybe there's 3 or 4 things going on. Let me look at the easy stuff first. And lastly, why we're doing this is, once again, just to increase the overall knowledge of everybody in the company. So then you sit here and you say, well, why would I want to be here? For those who know me, I use the term career. You know, none of you guys are here part-time. Some of you probably been doing as long as I have. So this is your career. So if you could learn more, it's just going to help your career. It's going to benefit you. It's going to benefit the company. And the knowledge, like I said, when you're putting the stuff in, you can sit back and say, okay, I didn't design the building. I'm not here to turn you guys into engineers, but you can say, okay, I can see why this is this. With that said, let me go, as Ted did his background, I'll go into my background. Some of you guys know me. You probably heard this story 1,000 times. I apologize. But for the few who don't know me, here's a little background on me. I'm 62 years old. I started in 1982 with a consultant engineer doing HVAC systems. Back then, you did everything by hand. You drew by hand, you calculated by hand. The architect gave you a blueprint, and you had to cut a piece of Mylar, and you had to draw your own building if you wanted to do your blueprints. So you got to learn buildings pretty good, and doing things by hand, you got pretty good at doing load calculations. There's computer systems now. I'm not here to turn any of you guys into doing things by hand, but the one advantage of doing that by hand was I could put something in a program and, the saying garbage in, garbage out. Hey, that doesn't look right. Maybe I made a mistake. So you have a sense for where it's going before you even use the program. After that was 8 years with the consultant. I went to Sikorsky Aircraft in their facilities department. I was there 6 years. Interesting time. When I walked in the department, there was 30 of us. We had one computer. When I left, everybody had a computer on their desk. So you got used to the Microsoft programs, Word and Excel, and got a pretty good background in the industrial world. For me, I like the private world. You know, the big corporation, was it a good experience? Yes. Was it a bad experience? You know, I like this end of it better than just being a number. My remaining years after that has been with mechanical contractors. This is the third company I worked for. I worked for a company in New York, AMX. When I walked in the door, they were doing $3 million a year. When I walked out, they were doing $50 million a year. And through that whole progression, they only hired one more person in the office. There was only 5 of us. And the biggest job I ever did was down in White Plains, the Ritz-Carlton, 1 million square feet, twin 46-story towers. I had 250 guys working on that job, 2,000 fan coil units. It was a 4-pipe system, chillers, boilers, the whole 9 yards. Was it a great experience? Hell yeah, it really was. I enjoyed it. But we were working 7 days a week for 18 months straight, and driving into New York, an hour in, 3 to 4 hours home every night, wasn't the long-term plan for me. As I mentioned, I've been wanting to do this for a long time, since 2009. That's 15 years. So I'm kind of glad that I get to start this off. I've never taught a class, so stick with me, guys. I'm going to try not to jump around. That's kind of why I got an outline here, and we'll go from there. With that said, let's start. And I really don't know what everybody knows. So what we're going to do, the trip we're going to go on, I'm going to start at the beginning. We're just going to start, hey, BTU, heating load, cooling loads, and just a 10,000 foot view. How do you calculate that? You know, how do I know how many BTUs for heating in a building? How do I know how many BTUs for cooling? And you get a little bit of a sense, and you might go into a building and it's the summertime and it's really hot, and you might say, okay, yeah, there's something wrong here. The unit's way undersized, because maybe some things weren't taken into consideration. Like I said, I'm not going to go into anything too deep. When I'm all done, if you want to ask some questions, not a problem. But the trip we're going to go on, like I said, in the very beginning, we're going to talk about heating loads and cooling loads. We'll get into a little bit of CFM. After that, the next session, we're going to talk about ductwork. You know, how to size it, static pressure drops, and things like that. I don't know if someone in this, we're going to kind of do I talk, and then someone else talks, and we're going to try to pair, whether we talk about duct layout, someone come up here and do duct layout. After that, the next session, we're going to get into piping systems. How do you select GPM? How do you size pipe? Pumps, fans, those kind of things. Why are there different types of fans? Why would you have an inline fan versus a utility set? Pumps. Why would you have an inline pump, an end suction, or a horizontal split case? They all have their place, they all have their purposes. Once we've learned how to size things, the load, ductwork, and pipe, then we'll get into systems. And we'll talk about ducted return systems, open plenum, piping systems, reverse return, primary, secondary. So there's how I want to build on it. And then after that, we'll get into equipment selections. Once again, nothing too heavy. We'll talk a little bit about chillers, boilers, cooling towers, plate frame heat exchangers. Some of you guys that were with me at Streetworks, you have open towers, you have closed loop evaporative towers, you have dry coolers. They each have their place, they each have their temperature differences, they each have their efficiencies. Why would you use it? What is this? We'll talk a little bit about condenser water systems. We got a big job coming up starting in end of May, June, that it's a condenser water system. It's got a little bit of a wrinkle to it. I never done one where they actually pump hot water to it, and it's got a hot water coil in it. So we'll see how that goes. I'm not sure why, but that's the system that they selected. And then lastly, we'll just talk about miscellaneous items. And real quick, louvers, plenums. You want to size a louver, especially when it's fresh air intake. You don't want to suck water in. If I have a 10 foot by 10 foot louver and it's for fresh air, My plenum off of that shouldn't be a foot long, deep. It needs to be deep enough so that you get the velocity across the entire face of that louver. If the plenum's too shallow, you're gonna suck most of the air from the center, let's say, of the louver. You're gonna have a higher velocity, and then you wonder why you got water in your ductwork. We'll talk a little bit about, fire dampers, fire smoke dampers, the different type of unit heaters, flues, vibration isolation, insulation, vapor barriers, fire stopping, pressure testing, and when you put the unit in, you always want to make sure that there's access to get to the filters and the doors. I can't tell you how many times I've seen a VAV box, and there's the control box for it, and the sprinkler guy ran it 1 inch off the face of that door, and you sit there and you go, why? Really had to do that? And then we'll just touch a little bit on the subcontractors we use, and how important they are for our success. I had a foreman one time, and he used to, I go, listen, the subs, they're part of our team. If they fail, we fail. And we're all here, we don't want to fail, so we got to work with our subs, keep them informed so that they can help us have a successful job. Lastly, through this whole thing that we're going to go through, each system, as I mentioned, has its place in a building. There's hundreds of different combinations to heat and cool a building. Just because you do one system somewhere in the building, you're not locked in with doing that elsewhere. Hey, you could have rooftop units, you have split systems, that kind of thing. You could have electric cabinet unit heaters and vestibules. So it just comes down to the building type, what's the construction, the owner who's building it, if it's new construction, what's he gonna do with the building? Is he gonna own it forever? So now you might wanna look at operating costs, energy efficiency. Is he gonna build it and flip it? Some guys just want, okay, I want a decent system, but it's first cost. I don't wanna spend a lot of money. So listen, with that said, everybody, we'll get into what I call session 1. Building load. So general information in our industry, there really is only heat. There's no such thing as, there's the term cold, but it's just something that has less heat. And I'm gonna do a little experiment. Here, I'm not gonna pick on anyone in the front row. Here, put your fingers from your right hand in there. All right, well, put them in, just put them in for a second. How does that feel? Cold. Cold, all right. All right, now your left hand. Put your fingers in there, here. Put your coffee down, because you're gonna hold this. I want you to keep your fingers in there for a little bit. For your left hand, all right? Well, first of all, how's that feel?
Colder.
Colder, okay. So as I said, there's only heat. Heat is gonna migrate from a higher temperature to a lower temperature. So obviously, in the winter time, if this is the inside of your house and here's the outdoors, sorry about that. As you heat up the inside of your house, the heat's going to transmit through your walls, through your roof. In the summertime, it's the opposite. This is the out, and here's the in. It's going to go through there. All right, that's long enough. Ethan, all right. Now here, now put that hand back in that one. How does that feel?
Lukewarm.
All right, but you said it was cold before.
Yeah.
So it's relative, that just has less heat in it. Okay. All right, so now that we know that heat migrates from higher to lower temperatures, you say, okay, how do you do a heating and cooling load? Well, the first things you got to do is you're going to look at your building, okay? And I think in the example that I have in there, let's say the building's 100 feet by 40 feet. So there's the building. Then we want to say, what is our design temperatures? In the winter, let's say it's 5 degrees outside, and we want to maintain 68 degrees inside. And in the summer, let's say it's 95 degrees outside and 75 degrees inside, okay? So we determined our temperatures. Now, the temperature differences here, that's 63 degrees, and that's 20 degrees, okay? So now we have our building, and what we want to look at the building is the length, width, and the height. I just kind of threw in there, you'll read, because we got to consider glass. If you have a window, let's say on the side of the building and there's an overhang and the sun can't hit it, we'll go into the solar part of that on the cooling. But you want to just review your building. You want to review the orientation of the building. Let's say this is north, this is south, this is east, and this is west, because you're going to need to know that, not for the heating load, but you're going to need that for the cooling load, okay? So once we have that, and let's say the building's 10 foot high, we want to calculate the areas. In my example, I think I had so many 6x4 windows. So if you said, well, what's the wall area? Well, I got 40, 40, that's 80, 100, 100, that's 280. So I got 280 linear feet of walls, 10 foot high, I got 2,800 square feet of wall. If I had 240 square feet of glass total, you know, then you got 2,560 square feet. So that is the transmission area of the walls. Let's say we had 240 square feet of glass, that'll be the transmission area of the glass. And if you have 100 by 40, you got a 4,000 square foot roof. All right, so you got that and you say, okay, where do we go from there? The next thing is you got to look at what the R value of the structure is. And some of you are familiar with R, whether you know it or not. You know, if you buy a roll insulation, it's an R8 and an R10. Well, what's the R value? It's 8 or 10, right? Let's say we have, our wall is brick, we got a piece of plywood, we got a stud, and then we got sheetrock. Each one of these has an R value. And let's say in the stud there, that's where the insulation is. So you get the R values of these things and you come up with R total. You add them all together. And the example's in the book. And R, it's just a measure of thermal resistance. So once you have that R, you'll see in there, we talk about U values. U is basically 1 over R. So let's just say the total, to make the math simple, the total R was 10. So U equals 1 over 10 equals 0.1, okay? So once we do that for the wall, we do that for the roof, and we do that for the glass. All right, so now we come up with our U values. And what we're trying to calculate is the sensible heat loss of this building. There's 2 types of heat in air conditioning. We're going to talk about sensible. That's the heat that rises a substance temperature without altering its physical characteristics. So right now in the heating load, we're talking about sensible heat. The other one is latent heat. And latent heat is the hidden heat it takes to change water vapor. So we're not going to be concerned with the latent load for our discussion on the coming up with our heating for the building, but we're going to talk about it in the cooling mode. So that's why I want to go over the heating load first, because it's simpler, and the same thing you do for heating, you do for the cooling mode. But then you got to do a little bit more. So in the heating mode, we're looking for the Q, which is BTUs, British thermal units. That's, once again, it's just a measure of heat. It's the amount of heat it takes to raise 1 pound of water 1 degree Fahrenheit. So if a gallon of water, 8.3 whatever, let's just call it as 8 pounds, it would take 8 BTUs to raise that gallon of water 1 degree Fahrenheit. You want to raise that gallon 100 degrees, well, there's 800 BTUs. You got 10 gallons, there's 8,000, and just on and on and on. So Q equals the area times the U value times the delta T. So in the winter, we said for the walls, we had 25 60 square feet, times the U, let's just call it 0.1, times the delta T, which is 63. Now, I'm not gonna do the math that fast in my head, but let's just say that comes out to 15,000. All right, just for a number's sake. You do the same for the roof. The roof, we said the building's 100 by 40. We got 4,000 square feet. Let's say there's a bunch of insulation on the roof, and you come up with the sum of the R's, you do 1 over R is U. Let's call that 0.05, right? Times the same 63 degrees. So let's call that, that's 200, and let's just call that 1,200, just for fun. We have the windows for transmission in the winter. We're not really concerned about the exposure, north, south, east, and west. You say, well, you know, during the winter, the sun's shining through the glass. Well, what happens when it's nighttime? What happens when it's cloudy? You're looking at the worst case condition here. You know, it's 2 in the morning, how much heat you're gonna need for your house, that kind of thing. Or how much heat, even though there might be a night setback in the building, you still gotta calculate the heat loss. All right, so we're not concerned about the solar. So if we had 240 square feet, let's just say, and you could find the U value of glass if you buy the glass manufacturer. A lot of these things are online. Let's just call that 0.5, because the transmission through glass is gonna be much greater than it is a wall or a roof. Times the 63 again, so that's 112. Well, let's call that 7,200 or whatever, right? So we're gonna add all these up, and that's gonna add up to the heat loss of that building. After that, if this was an office building where you gotta be concerned with outdoor air or infiltration, when you look at the construction of the building, you know, it's a renovation, it's an old building, we're gonna have some infiltration. It's a brand new building. I mean, nowadays when they're doing, you know, all these LEED gold and passive house and this and that, the buildings get really tight. So now you're seeing a lot of these apartment buildings we're doing, you know, back in the day, you really didn't introduce outdoor air into the apartments, but now you have to because they're really tight. So you come up with the, let's just call this 23,000, and you say, all right, I got 10 people, I'm gonna bring in 10 CFM of outdoor air. So the Q for the outdoor air equals the number of people by how much CFM per person times the delta T, because you're bringing in 0 degree air. And then there's a factor of 1.1 that you multiply it by. So if I had 10 people by 10 CFM, right, that's 100 times 63. Now I'm at 6,300 times 1.1, let's call it 69, call it another 7,000. So now I got 30,000. So I'm sizing this system for 30,000 BTUs. And that's in per hour measurement. So once you have that, and you say, okay, I'm gonna put a boiler, I'm gonna put a gas-fired rooftop unit, you need the 30,000. If the rooftop unit has a certain efficiency, you know, let's say it's a 0.8, you know, you're gonna be getting something, you know, let's call it 36,000 in, 30,000 out. So that's the heating load side of this.
Ed, what about the people adding the BTUs to the space? You got 10 people at how many BTUs per person?
Well,
That adds to
it comes to the activity level.
Right.
But for me, when I do the heating load, and once again, let's say it's midnight, let's say there's no one in the building. I don't calculate the lighting load. You know, in air conditioning, we're gonna calculate the heating load of the people. And when we're doing the cooling load, we're gonna calculate the lights. Once again, if you gotta heat this building in the middle of the night, there's no one there, the lights are off, the computers are off, the machinery is off. A lot of things that you consider when you're doing a cooling load, I kind of say, hey, listen, you know, there's such diversity, you know, even if you're gonna consider the people or the lights, you're gonna consider them all, you're gonna consider some. At that point I say, you know, you got such a large delta T here, the heat that you gotta put into the building, some of those other things could be negligible, and I don't think about it. But when you come to cooling loads, all right, let's go back to our same building. Now you've already calculated the R values, you've already calculated the areas, you know those, you don't have to do it again. So the transmission, once again, it's 95 degrees out, and that's trying to pour into the building. You're 75 degrees in, so there's your 20-degree delta T that you have there. You got your north, you got your south, you got your east, and you got your west. So in the cooling load, you got to calculate the wall transmission, you got to calculate the glass transmission, you got to calculate the glass solar. Right? You've all driven in your car on a long drive and the sun's beating in on the driver's window, and yeah, you got your air conditioning on, but man, I'm wearing a short sleeve shirt, my arm is roasted, right? That's one thing that you take into consideration. In the glass solar, you got to look at each exposure. So you're going to have a glass solar north, south, east, west. All right, so let's just say the north was and it's the same thing, you know, with the wall, it's still Q times the area times the U times the delta T. So this is the same as you did in the heating, it's just that you're going to use 20 degrees there instead of the 63. You're going to do the same for the roof, and you're going to do the same for the glass. All right, you're going to use the transmission. Really doesn't matter what the exposure is. Hey, it's 95 degrees outside, 95 is trying to get in all directions here. So you're going to take that 240 square feet times U, which we said was 0.5 times 20. You know, the roof, for me, if it's a flat roof, depending on the color, and I don't want to get, once again, there's books where you can get into the angle of the sun, and we're not going to get into that. But depending on the color of the roof or what, I like using a slightly larger delta T. I might use between 30 and 40. Normally roofs, especially new buildings, are so well insulated, the roof load is possibly could be one of your smaller transmission loads. So I like to use something a little, let's say we're going to use 30 there. And if we said the roof was 0.05 and we had 4,000 square feet, all right, so I got my transmission of the roof, I got it of the walls, I got it of the glass. I come here and I say, let's say there's, all right, we're trying to calculate BTUs, and let's say there's 40 square feet of glass on the north, 40 on the south, let's say 80 and 80. Here's my 240 square feet. So once I do that, I now have to look at a book, and the equation for solar is Q equals the area, shade coefficient, times the solar heat gain factor. Now that stuff's in the book. So now you sit there and say, okay, this is, you know, not to get in deep, but could be some of your larger loads. And what it's going to tell you is you're going to look at, you know, they don't have, in the example I have, they don't have 42 degree latitude, so you can pick 40. It's going to say in the north, it's going to say in the worst time of the month, hey, that's, let's say the shade coefficient, let me just back up, is 0.4. You got to look that up for the glass. You know, is it single pane? It could be 1.13. Is it double pane glass? Is it insulated glass? And that's what this number is. And then the other one is per exposure. The north could be, let's say, 100. The south could be 200. And the east and west could be, let's say, 235. So you're going to come and you're going to do that math, and that's going to give you the Qs for those. So far you're going to add the Q of this, and all that. So now we're going to get into things that we didn't consider in the winter. That's people. And in the book that I gave you, there's a chart. And it comes down to activity level. But now the people, this is all sensible load, sensible heat. People give off a sensible and a latent. Here's why you need a big board. So there's people sensible heat, and there's people latent heat. And it comes down to activity. Right now, you're not giving off a lot because you're sitting. When you guys are working, you're giving off a lot. If you're dancing, if you're running, if you're at a gym, you're giving off a lot. So basically, it's just the number of people in the building by the sensible heat gain that you get off of off the chart. And let's just say this was an office, so let's call it 250. And in that example, sometimes the latent heat is 250. So we calculated the latent heat, the sensible heat and latent heat for people. Then we're gonna look at lights. All right, it's an office building, we got so many watts, blah, blah, blah. Let's just say it's 1.5 watts per square foot. 1 watt equals 3.413 BTUs. So when we talk about electric heaters, oh, I got a 10 kW, right? 1 kW is 3,413 BTUs. 10 kW would be 34,000 BTUs. All right, so I got 1.5 watts per square foot. I said I had a 4,000 square foot building. Yeah, I got 6,000 watts. 6,000 watts times 3.4, you're probably in the 20,000 BTU range. So you calculate the lights, you calculate the people. Last thing, since it's an office building and we're calculating once again at the word, and you do the same for, let me back up, you do the same for appliances, you do the same things for computers, copiers. You know, you look at the back of the computer, it's gonna tell you how many watts it takes, your screen how much does the copier put out. So you wanna calculate the heat generation of all that equipment that's gonna go into your calculation. But once we get that done, the last thing we gotta do is we're introducing fresh air. You bring in 95-degree outdoor air, you gotta cool it down, but you also know that there's moisture in it. And once again, just like the people, that's the moisture content. You gotta calculate moisture content that you're wringing out of that outdoor air. And the same thing, all right, if we had 10 people and we're doing 10 CFM a person, you got 100 CFM, all right? So we got 100 CFM, and this is the sensible, and this is the latent. Now the sensible is easy. Times 1.08 times the delta T. Delta T we said was 95 to 75, all right? So let's just call that 1. So there's 100 times 20, hey, there's 2,000. The latent load's a little bit in depth, but they have a factor of 4840, and it's time what they call delta W, which is the humidity ratio, so many grains of water per pounds of air. I've always used calculated so many times, and a lot of times it comes out close to the same number. Let's just call that 2,000 as well. So now we've calculated all the sensible loads, we calculated all the latent loads. Okay? So you got your sensible heat, you got your latent heat. You want to keep these numbers separate. And I'm not going to go any further on that until I just get into the next portion of the talk. Before I wrap this up on this session, there's other factors when you're looking at a building, and some of them are really important. And probably the biggest one is vapor barrier. You know, you got an old warehouse type building. Let's say you guys, some of you have been at Nutmeg Spice, right? We did that job. Now that building had a vapor barrier, but it was in bad shape. They had to fix it. But what that vapor barrier does, it's trying to slow down or retard, this is the building on grade, humidity. Once again, it wants to go from higher to lower, and it wants to scream into that building. And if you didn't have a vapor barrier, you can imagine the entire square footage of the walls and the roof, all that humidity wanting to come in, and you're air conditioning this thing. So while you're air conditioning it, you got a higher humidity content, and your AC unit is trying to handle that bombardment of humidity. And you go out and you look at the unit, and the condensate drain looks like someone turned on a fire hose. And then you wonder why it's hot and sticky in the building, because the unit's been overwhelmed. So when you're looking at a building, you always want to make sure, let's say you went there and a guy's saying, yeah, I'm thinking about renovating this building. It's like, well, I don't see a vapor barrier. You know, well, how many tons do I need for this thing? Well, you know, if the building's in Oxford, we're gonna try to dehumidify Oxford. So that's a tough one. You know, I suggest, you know, for efficiency and everything else, you either install a vapor barrier, or if they have one that's in bad shape, you wanna get it fixed, okay? I just have a little, you know, we talk about relative humidity, and that's what some of this has to do with. I just put the definition of that. That is the amount of water vapor actually in air expressed as a percentage of a maximum water vapor the air can hold at the same temperature. And you say, what does that mean? Well, hey, it's 95 out. We've all been out 95 and it's 85% relative humidity. The warm air has a better chance of holding more humidity. Vice versa, when it's 5 degrees in the winter, you know, what's the relative humidity? 10%? The air doesn't have the ability to hold that kind of vapor. So a lot of things that we're talking about there, you've probably heard the term relative humidity. You know, like a design, hey, I want 75 degrees inside. That's called dry bulb, and there's a wet bulb. But a building, you want to probably, an office building, you want to be below 50%. Are you going to get it in the summertime, unless you put specialized equipment in, you know, you're never going to be 75 and 10%. You probably wouldn't want that either in a building. You know, there's a comfort zone. You know, you can withstand higher temperatures in a building if you know, hey, being 80 and 30% relative humidity isn't bad. 75 and 50, 75 and 40, not bad, right? If anyone's ever been to Arizona, it's 120 degrees. Oh man, it's a dry heat. It's hot, but the relative humidity at that point, because it's so hot, is so low, it's not oppressive. The only thing is if you're outdoors all day long and you go in, you'll see that, you know, and you've been out there for a long time, your lips are chapped and you're dying of thirst. So I just wanted to touch on that. So the second session I want to get into is just not so much equipment specific, but hey, I want to size a unit, whether that's a rooftop unit, a split system, a VRF system, no matter what. How do I do it? I calculated those two loads. What do I do with it now? And I don't really remember the numbers exactly. I probably could look at it here in the example. Just real quick, you know, Steve kind of liked the little smiley face. There's just a little illustration of the heating load, right? You know? Now, if you're doing a home and you got a basement, you know, and you want to calculate the heat loss there, you know, the basement most likely is below grade, or the grade, you know, after so many feet is 50 degrees, 55 degrees. You just wind up using a different delta T there. And for the foundation, you don't use the slab, you don't use the whole slab, you just use a couple feet along the perimeter and you do that calculation. With that, you know, here's the 100, the 40 by 100 by 10 foot high, kind of the example. So like I said, you got your wall, you got your glass, you got your roof, you got your slab, you got your infiltration, and you got your BTUs. You see there's more on this for the cooling load. Just to go over it quick. You got your transmission, you got your solar, you got your people, you got your appliances, you got your computers, you got your lights. And then there's just a quick calculation. And I got sensible and I got latent. So now that we're going to go into sizing something, whatever unit is, it's expressed in tons of air conditioning, which is 12,000 BTUs. Okay, I got 12,000. I got these two numbers. What am I looking at here? The total cooling of your AC equipment is sensible heat plus the latent heat. Okay, so in this example here, we're saying the sensible heat is 135, just gonna round it down, 135,000 BTUs. And the latent heat, we'll just call it 11. So my total cooling that I'm gonna select this unit on is 146,000 BTUs. You divide that by 12,000, and in the example, it's 12.2 tons. Let's just call it 12.5 ton unit. So if you're doing a rooftop unit, you're picking a 12.5 ton unit. And the unit, and I put some examples in the tab 2, just of some submittals where you're gonna see this data. You're gonna see the sensible heat, you're gonna see the latent heat, and you're gonna see the tonnage. All right? You wanna make sure, because depending on the mixture of the building, hey, you got a theater, you know, and you got 200 people in, and you're bringing all that fresh air, that building percentage-wise is gonna have a higher latent load than, let's say, a warehouse, which is gonna have very little. You got a warehouse, hey, talk this shop, you got 3-4 guys working it, look at the size of this. Can you imagine if this was an office, how many people, how much latent they'd be putting out, how much outdoor air I gotta bring in? So you could sit there and say, hey, I got 12.5 tons, but if, let's say, 40,000 of that number or 50,000 was the latent load, you know, a lot of air conditioning units, you'll see, you know, that this maybe on a standard unit is 15, maybe 20% of the total tonnage. And you say, geez, if the latent load was 40%, if that was the case, I gotta make sure I satisfy that. You know, this might be a 15-ton unit then. I don't wanna get too deep, but that's, when you're looking at these, you wanna make sure you get this. If you get this, most likely you're gonna get that as well. But the ratio of that, of the total cooling, could be all over the map depending on how you size your building. Okay. All right, I got my unit, whether it's a rooftop or split. And then what do? Well, I need to know the CFM. And I know there's a lot of, you know, hey, 400 CFM a ton. That's a nominal term, it's not exact. If you looked at, if you were selecting equipment on a 12.5 ton unit, you know, okay, if I just arbitrarily said, hey, you know, that's about, let's say 5,000 CFM, right? You look at the chart and it's gonna tell you how much cooling. That unit might be able to give me 6,000, might be able to give me 3,500. So there's a range. It's not a set in stone 400 CFM a square foot or per ton. But when you calculate the CFM of the unit, since the room is generating the sensible load, even in cooling, just like heating, the sensible load is what you base your CFM on. So if I have 135,000 BTUs of sensible load, that's what I'm going to calculate that on. And the example is, all right, CFM equals the BTUs divided by the room delta T, and I'm going to go over that, times 1.08. And you say, what's the room delta T? Well, in our example, I'm trying to maintain 75 degrees of the space. This unit, let's just say, is going to discharge 55, 54 degree air. So let's go 54. So the delta T for the air is 21 degrees. If I go 21 times 1.08, divide that into the BTUs, the correspondent for this example is 5958 CFM. So now, okay, I'm getting close. I know my sensible heat, I know my latent heat, I know the tonnage, right? I know I want to select a unit that can give me almost 6,000 CFM, all right? If you were looking at a building with multiple rooms and you wanted to know the CFM for each room, you just take this overall calculation and do mini calculations. Hey, you know, on the 4,000 square feet, I got a room that's 400. Hey, if it's in the interior, it's gonna have less of a sensible load because it doesn't know the exposures, but if it's a corner office, it's gonna have a little bit more. You just calculate the sensible load just for that room, divide it by this 21 times 1.08, and if you did that for every room, you should be pretty close to that number. So that's when we get into duct distribution and how you size ductwork and everything else. But that's how you get to that number. So you say, okay, Ed, we got the CFM. You base it on a sensible load. you told me about total cooling and this latent, what's happening there? Well, that latent load's happening at the AC unit. That's why condensate comes out. Remember, it's the energy required to change the state of water vapor, right? So you're dumping this 54-degree air into the space. Once again, heat migrates from a space of higher temperature lower. So it's not like the cold air is making the room cold, it's actually absorbing the heat. It's extracting the heat, and we're gonna reject it out at the rooftop unit. So we're sucking the heat out of the space. But while it's doing that, it's also picking up the latent heat, the moisture that you're putting out. So up at your unit, you know, you got your fan, you got your ductwork, you got your return duct, you got your coil. Yeah, you're bringing in some outdoor air. I think not that we'll get into in other sessions, but when it's really hot out, you want to bring in your minimum amount of outdoor air per code, because you don't want to do 100% outdoor air because it's 95 degrees and it's humid. So in our example, we had 10 people, let's say, and 10 CFM. So out of this 5,900, you're only bringing in 100 CFM. So your mixed air temperature is probably not too far off what your return temperature is. And let's say in this example, I'm maintaining 75, my return air is going to be 78 degrees. Well, when the DX system's going on, what it has to do is it's taking that mixed air and it's got to bring it right down to the dew point where I'm going to super saturate that air. I'm going to make it so cold, and the energy, the latent heat portion of it, the sensible is taking it, let's say, from 78 to 54 again, but the sensible load is giving that little extra energy to turn that vapor into water. And that's what comes out of your condensate trap. So that's why that portion is important. And as I mentioned, with a building with no vapor barrier, can you imagine, you know, at that point, it'd be like taking the outdoor air, relative humidity, and pumping it through the system. This unit's gonna say, hey, wait a minute, you know, I was only 15, 20%. Now you're eating up 60%, because now I'm gonna steal some of this sensible load to change this temperature because I'm struggling. I'm trying to make more water than we thought we were gonna make. And that's when you have a bad situation. But that's where that energy is happening at that unit, to bring the moisture out and deliver the air to the space. Now, when the air comes off that coil, since we turn some, you don't get all of it, but you turn some of the vapor into water, it's actually coming off that coil saturated. It's almost 100% relative humidity, but it's cold. So when that cold air enters the space and we're absorbing the sensible heat load, we're not going to get into the site chart. I'll bring one in, I'll give you one, guys, one just to look at it. But when you add sensible heat to air, the psychometric chart is kind of like this. This is the saturation line, and you have all these humidity lines. You know, there's 100%, let's say here's 50%. Well, I'm 54 at 100, but now it's going to get heated up to 75. These are the temperatures. Let's say there's 54 and 75. It dries it out. We'll get more into that when we go to do more for nutmeg spice. They have to have humidity control, reheat systems. You know, if you wanted to dry a space out and you really wanted to dry it out, and you say, well, I don't need a lot of cooling, but to get the humidity out, you gotta get that air to 54 degrees, 53 degrees. If I dump that in a space, and let's say it's an interior space that doesn't have a lot of heat generation, you're gonna freeze them. Not only that, you're gonna change the humidity. Sooner or later, there's no heat for this to get absorbed, so you actually turn that room into almost 100% relative humidity. You reheat it. I'm gonna subcool it, I'm gonna wring the moisture out, and then I'm gonna reheat it. You know, like I said, nutmeg spice, you know, some of these rooms, they wanna maintain 70, right? We're probably discharging 68-degree air, because there's no load in the room. But I gotta wring the humidity out. If not, their hopper with their spices in it turns into a concrete block. You know, they put the spice in the hopper, it goes to a bottle, or this, and this. And when you reheat, it's a sensible heat. It just drives the humidity right out of it. So, with that said, gonna wrap it up here, guys. I got some other equipment factors. like I said, when we talk about, we size the unit, we know the CFM. When we start talking about duct design, the only other bit of information you gotta give someone for the unit, whether it's a split system or rooftop, you gotta calculate your total external static. And that is the static, you size the duct for a certain static pressure. So you gotta take into consideration the length of the duct, the elbows of the duct, the transitions of the duct. Do you have dampers in the duct? Do you have a VAV box? Do you have a HEPA filter because it's a hospital down by the operating room? You gotta calculate that whole external static. And when you look at the examples in the unit, they have total static pressure, external static pressure, and then internal static pressure. You're calculating this, right? And you call up, I know you hate Train, but we'll use Train. I'm gonna use a Train rooftop unit. You call the guy up and go, hey, I got a 12.2 ton rooftop unit. I got a sensible load of 135. I did my heating load. Hey, it was 30, 38, 40,000 BTUs. I needed to give me 59, 58, let's just round it up to 6,000 CFM. And my external static pressure is 2 inches. Let's say it's not a big system, but I got a ducted return. And I only have a supply fan, so I gotta calculate not only, well, I gotta calculate the whole loop. I gotta calculate the pressure drop from across the register, the supply and the return. So you give them this number and you say, and it's expressed in inches of water column. So I would say, I need it to give me 2 inches. The internal static pressure is derived from the Train unit. They have a certain drop across the coil. They got a drop, let's say it's a gas fired heat exchanger. They got a drop across the return and the outdoor air damper. And I want a MERV whatever, 13 filter. And that has a drop. So he's gonna say, hey, let's just say that's 1.5 inches. So the total static pressure drop in that unit is 3.5. You only gotta tell them this. So to wrap it up, where do we go, right? We calculated, we got an idea how to calculate a heating load. And I'm gonna have to tell them, you know, once again, how much heat I need for that unit. We calculated a cooling load, which is kind of the same as the heating load with a different delta T, but then we're gonna consider people lights, outdoor air, infiltration, and the CFM. But once again, since we're talking in summer and we're concerned with the humidity inside the space, we gotta calculate the latent load, which is a separate number that gets jammed together besides the unit. So I wanted to start at the beginning. So the next one, we'll talk about ductwork, and then after that one, we'll talk about pipe. All right, so now you know, okay, we're gonna have a duct main that's gonna handle 6,000 CFM, and it's gonna get distributed right to the corner office, which is a conference room, and we're gonna be putting 800 CFM in that. And we can talk about how we do that, and then we'll talk about how do you calculate the static. You know, once again, you got an engineer, we do plan and spec, and you know, I got a rooftop unit, you know, and I'm just gonna draw a duct like this, so I'm gonna put a bunch of that, right? The external static on that is 1 inch. And then they say it's up to us for coordination, all right? Oh man, I gotta get around the roof drain. I got, oh man, it's got a low steel, and before you know it, you wind up putting 20 elbows in that system. And you got 2.5 inches of external static. And when your balancer comes and says, yeah, you know, you're only getting about 3,400 out of that unit, right? Hopefully the engineer figured out some real world situations. I had a job, we had 8-inch chilled water pipe, and it was going about 300 feet. And once again, the engineer drew it like that. You know, I had over 14 elbows to get from there to there, getting around low steel and coordinating with other trades. So when you're telling, and we'll get into it, but when you're calculating external static, hey, you look up there, no mystery. What do you think the external static of that is? Almost nothing. Almost nothing, right? When we're going to use a ductilate or whatever, you size it for inches of loss per 100 feet. You know, you'd size that at a 0.1 or a 0.08. So what do we got there? 20 feet. Even if we did it at 0.1, you know, now you're talking 0.025. let's say the grill is 0.1, you know, there's not even, okay, we put a filter on it, let's call it a 1/4 inch of static on a system like that, you know, real simple, you can see it. But if you were in an office building or hospitals, the engineer might draw, you know, 15, 20% fittings on that. I've done hospitals and they're like 45% fittings. And you're just sitting there saying, hey, I hope you figured enough. I was talking to some of these guys, we did a job at UConn, and we got stuck fixing the exhaust. It was a servery. You know, they had all these hoods, you know, they'd have the Chinese and the Italian and this, and each had a hood. And they had all this ductwork, you know, double wall stainless steel going to these utility sets up on a platform. And the engineer had 1 inch of static, right? And the hood itself was 1.1 inches of loss. All right? UConn didn't want to hear it. They said, we got to correct it. We argued with them. We put in a change order. We fight. You know, but you got to correct it, because if you say I'm not doing it, well, we'll go hire someone else. Now, if you're going to get stuck with it, you just you have no control over costs. That cost me $150,000. They just, you know, it's kind of like asking your dad, can I borrow the keys? You're going to pay him this change order? No. Can I have the card, Dad? No. Why? Because I said no. You know, am I going to sue him for $150K? So big things can happen if you don't calculate that right. The last thing I'll say, just as an example, I talked about HEPA filters with operating rooms. Right? You know, you got the system, and then over there you got the operating room. You know, a real efficient HEPA filter, when it's clean, is going to have a 1 inch drop. Right? And as that thing starts getting dirty, you don't throw it away till there's 2 inches of loss. Can't tell you how many engineers, oh, it's got 1 inch of drop. So you're expecting me to change that HEPA filter every 3 days. You know, that HEPA filter might cost you $800. You have to consider, even when you know, if you were going to calculate that you got filters in the system somewhere, you're not going to calculate that the thing's blocked, but you got to calculate that there's a load on there. Because what happens is, when we talk about fan curves, it's CFM versus static pressure. As the static pressure goes up in the system, you're going to get less air. And you got a system that, when it's clean, it's that, and it's dirty, that. You add another inch to a system, you're getting hardly anything in that operating room. So once again, something to consider from the service end and everything else. Hey, you know, we're doing work at a medical center, and they got a HEPA filter. You know, hey, we're not getting any air in here. First thing is, you got HEPA filters? Yeah, when's the last time you changed them? And you service guys know, when you go into buildings, what do you find 99% of the time? The thing's plugged solid, right? Just things to consider. So I'm going to finish there, guys. Like I said, just want to, if you get a little bit of sense of what's behind the design, you get a little bit of sense of how that equipment was sized. For the guys that put it in, you know, okay, I understand, you know, a little bit. Now I know a little bit why we're doing this. And from the service guys, you can sit back and say, okay, what's really going on? Is it a dirty filter? An O filter, or hey, you know, the
Like
air
coil.
conditioning, you know, we're air conditioned in this space here, and it's 95 out, and it's 85% relative humidity, and I open all these doors. There goes my vapor barrier. What do you think the temperature is going to be in here after an hour? You might as well be outside. These things, right? Yeah, you do it someday, and wherever the condensate goes, go look at it. And you're going to see the water pouring out of that thing, because it's trying to dehumidify Oxford. So,
And if you have a bank that's built on a concrete slab, and summer comes along, that wasn't in the calculation, all of a sudden dew point hits the floor, and they have
Yep.
slip hazard.
yeah. So, with that, guys, any questions? I don't know. Once again, I hope I didn't bore you. Everything I talked about and then some is in the book. The pages in tab 1 at the very back, this is out of ASHRAE. You know, once again, you could get really complicated. I tried to keep it simple. The equations we talked about are in there. There's some, you can look up charts you know, hey, there's wall construction, and it's basically pointing out, hey, for this, the R is this, for a brick, it's this, for sheetrock, it's this, for plywood, it's this. And that helps you calculate. For metal roof, the metal is this. The rubber roof, the rubber is this. You can look up all those things. So just to give you an idea of what something would look like, I mean, you're building a sandwich. The wall's a sandwich. You got your bread, you got your bologna, you got your cheese, you got your lettuce, your tomato. Each one of those has a resistance. What's the total resistance to the sandwich? And it has one. I don't know what bread would be, but you can come up with a U value for a bologna sandwich if you wanted to. Talk about R values for glass. Talked about the solar cooling load factor, shade coefficient. This one here, you look at the 40. I think we're at latitude 42.
Yeah.
They have 40 and 44. Let's just pick 40. There's your different exposures, and it's going to tell you what month is the peak of the heat gain through the glass for the solar. Heat gain through lights, I know I did the number of watts times the 3.413. There's just a little ballast factor. If it's fluorescent lighting, you gotta multiply that by 1.2. If it's incandescent, it's just by 1, okay? And then a little bit about outdoor air. And the second to the last page, you know, there's your chart. Let me find my glasses here. For people, all right? So seated at a theater, sensible heat, 225, latent heat, 105. Seated light work, 245 and 155. Moderate dancing, sensible heat, 305, latent, 545. Person sweating, here comes the latent. All right, bowling, right? I mean, athletics, sensible heat, 710, latent heat, 1090. So you're in the gym, you're pumping something out, you know, you're putting out, you know, you're seated at a theater, latent's 105, athletics latent's 1090. That's 10 times the amount of latent you're putting out. So you got to calculate all that. And the same thing with outdoor air. You're going to look at a chart and it's going to say, okay, you know, for an office it's this, so much CFM per person, but for a gym, you know, you're going to have a lot more required fresh air per person. You know, just because of the oxygen they're eating up and also the stink, okay? The next one that we'll do will be ductwork, like I said, and then we'll talk about fans and whatnot. So what we're gonna do through the course is we're gonna build a system from the ground up. And with that, any questions? I do appreciate you guys coming here. I hope through the course of this, you pick something up. I'll just end with, some of you guys know that when I got in this business, I fell into this business. I had a man named Harold Gorman who gave me my first job. I was driving a truck, I was working in a bakery, and they needed a draftsman. I went 1 year of college at UConn for fine arts, so yeah, I could draw. You want me to draw with a straight edge and a pencil? Well, that sounds way too easy. When I went there, I said, I really like this business. He was a man that had all the time in the world for me, and he didn't need to. He was a friend of the family. He didn't need to do this for me. So I feel I owe the world back what he did for me 1,000 times over. And I haven't really had the opportunity for a lot of people wanting to take me up on that. You know, some of the young men that you see in the office that came from the place I was last, I think they learned a little bit from me, and I get great pride in their success. But I really need to pay the world back. And I would just say to you guys, and given an opportunity, you see a younger person struggling, don't be afraid to put a hand out. They might not take it, but you offer it to them. And you teach them. You guys got apprentices. Take the time. Yeah, they're green. Oh, they're slowing me down. Listen, they're the future of this business. And for some of you guys that aren't apprentices, but you might be in your 30s, you're going to want that apprentice, you know, 5-10 years from now. You're hoping that guy's really good, because if he's not, the company you're working for isn't going to succeed, and we're all going to fail. So with that, I'll give it back to Ted.
I know Ed fed you with a fire hose, but there's a reason behind it. We want to build a good foundation, and this is foundational, and it may be a little bit ethereal.
This is the most we're gonna get
Yeah,
into
this
that.
is going to be the most of that kind of level of, I'll call it intensity for the design work, right? We want the practical, but we wanted to build a foundation. We wanted you guys to see, how does this actually happen? How does you actually get to these numbers? How does that happen? And why is that important? And he just gave it to you in a nutshell. This is all going to be up on the web. Every session that we do, I'm going to put on the employee portal. So if you ever want to go back and say, you know what, Ed was talking about something, I want to just revisit that real quick a minute, it'll be there, all right? But yeah, thank you for slogging through a university course, actually. But that's it. We're gonna go from there to the more practical end of things. We'll get into plumbing, pipe fitting, other things that you might be more interested in. I'll say it that way. Not that that's not interesting. To me, it's interesting.
Well,
I mean, I benefited from this myself this morning, so I'm grateful. But yeah, if you have any questions, anytime, just call Ed or call me.
You know, yeah.
Ed would be better.
If you want to talk to me offline, or I'm on a job site, like I said, everything I went over, there's a little bit more information. Other than the ASHRAE stuff, the other stuff I just typed up, just to try to follow. Whether I followed every word in every direction, I don't know. I'll let you guys decide. But you got the information. And as like Ted said, this was the foundation. The duct and the pipe will be more interesting, more hands-on, that you guys are familiar with. But we'll talk about, fan selection and pump selection and why you use this in lieu of that. And if some of you guys are gonna build a house someday, or you got a parent that doesn't have air conditioning, you sit there and go, you know what, let me just do a quick little load here. All right?
Yeah. Keep your notebooks, because we're gonna keep adding to them month by month.
Yeah, bring them, we'll give you, whatever the topic is, we'll give you pre-punched handouts, and you can just slip that behind the next tab.
Yeah. And that's it. We're set. Have a good day.
Thank you.
Thank you for coming.
Thanks, Ed. Thanks. That was good. That was real good.